Okay, folks, last learning goal for this module, and we're going to pick up with where we left off in our simple mechanism, and we're going to use this approximation called steady state approximation, which is a condition-specific approximation, but makes our lives much easier if we can apply this approximation. So let's go back to our simple mechanism that we have been playing with. So A goes to intermediate I with rate constant Ki, and then the intermediate goes to product with rate constant Kp. And so now there's a couple of things we have to consider for the steady state approximation to hold. We have to have a clear rate determining step. Okay? And to have a clear rate determining step, we need to go back to the situation where Kp is much, much greater than Ki. This step is fast. This step is, I was about to write stow. Let's write slow. And now when I add these together, it looks like A is just being converted to products, and that's occurring at the rate constant Ki, because Ki is rate determining. So this is all very good and qualitative, but can we prove this to be mathematically sound? All right. So here is how we do it. Well, we know that we can just write the integrated rate law for A at any time t directly, right? So that doesn't change, okay? And that's dependent on Ki to the e to the negative Ki times t. So, but now, however, when we go to write di dt, here's what we're going to say. We're still going to put together the full rate law. Ki times A minus Kp times I. But now, let's see how we can make this approximation. And we're going to use my model to help us visualize how that approximation goes. So in this case, we said Kp was much, much greater than Ki. So in my model here, that means K2 is much, much greater than K1. And here's what I want you to notice what happens. First of all, the reaction slows down a bit just relative to where I had it. Second, if we now look at my intermediate, and in this model my intermediate is B, you can see here it is being produced at a steady rate. So in other words, because we have a first step being slow, where I is lagging, and then as soon as I is produced, it's consumed, its rate of formation and its rate of destruction is roughly equal to 0. Okay? So, and we can see that from its slope right here. So now this allows us to make some adjustments mathematically, and that's going to go as following. So because I have this rate law all set to 0, I can now get an expression for I, an approximate expression, and just doing the algebra, adding that over to the other side and dividing by Kp, that becomes Ki over Kp times A. We already have an expression for A, right? We can plug that in right there, and we'll continue along with that. And I'll note that now this is I at time t equals Ki over Kp, and now that's times A initial e to the negative Ki times t. We still consider the rate of production of our product, dP by dt, which is going to be equal to positive Kp times I. And now we have an expression for I that we can plug into the product, right? So that becomes dP by dt equals, so let's see, that's going to be Kp times the quantity now, Ki over Kp, A initial e to the negative Ki times t. And you can see the Kp and the Kp will cancel, which is beautiful. And now taking this up to here, hopefully I left myself enough room. dP by dt equals Ki A initial e to the negative ki times t. So we still have to integrate this sucker. So, right, I still have to push dt over to the other side and integrate. So let's just show that step. So that's the integral of dp from some initial to some final. And that equals ki times a initial times e to the negative ki t dt. And so now I'm also going to integrate this from some initial to some final. And so carrying along with that here, we end up with the following. So initially the product is 0, so we don't have any. So, and then in the final condition, that's just going to be p, and I'll put the sub t so we recognize that's p at any time t. And now I can pull out ki and a initial out of the integrand. And I end up with the following thing to integrate, e to the negative kit dt. And I'm going to skip straight to the chase and integrate this thing over the limits from 0 to t. And I'll do the algebra, and we end up with the following. So this ends up going as p at time t equals a initial. And the result of this integral and doing some algebra, we get 1 minus e to the minus kit. And then remember, we still had our expression for the first order decay of a. That goes a at any time t equals a initial e to the negative kit. And lo and behold, this is the exact result that we would have got if we had only analyzed just this step, right? So I'll put that in a different color so we can see how that's connected. And I'll repeat that again. So if we had ignored this entire mechanism, right, and just recognized that the rate determining step is A times Ki forms products, and we analyzed dA by dt and dP by dt without doing any of the stuff with the intermediate, this is the exact expression we would have come up with, which is pretty awesome. And then hopefully what we can tell from our graph here, that C, we're getting this nice, simple exponential production. A, we're still getting our exponential decay. And now the rate of the intermediate is constant enough that this approximation is very reasonable. So when can we not make the steady state approximation? Well, if I start scrolling down K2 and making K2 approach that of K1, you can see now I've got a complicated rate expression for B, right? And if I do something like that, if I make them close enough to each other, I've no longer got this steady state approximation going on. And certainly if I go the other way and make K1 really fast and K2 really slow, so the opposite of this, I definitely do not have the steady state approximation. So again, steady state approximation says when our first step is very slow and our second step is very fast. I'll try to turn that up just a little bit so we can see it do some reaction. So in other words, when we have a clear rate determining step, and for simple mechanisms, that would be the first step being the clear rate determining step. Then the steady state approximation applies, and our rate law is consistent with the slowest elementary step. Awesome. Okay, that is it for this module. We are going to continue down the kinetics rabbit hole through the rest of the semester. Okay, I'll see you in the next videos.